Oh, what's this? Comiggle. Comiggle. What's comiggle mean?
Maybe they're symbols.
Calcium, magnesium, aluminium. Good. What are we going to do today, Mr. Park?
Let's react some metals.
All right. So we're going to react 3 different metals with water, and then later on in this lab, we're going to see how some of those metals react in the presence of fire in the air. So first thing your lab says is we are supposed to take and put about 30 mils of water into these beakers. So we put 30 mils of water into each one of the beakers. They're labeled. You can see this one is calcium. The one in the middle is magnesium. And the one on your right is aluminum. And the lab calls us to first put a piece of calcium in. So our calcium is stored in a container like this. Now if Mr. Park zooms in there, you can see that the calcium doesn't look like a typical metal. I know when I think about metals, I think about metals being shiny and having a metallic luster to them. And this definitely does not look like that. These are little nuggets. And it almost looks like it's whitish. It's like a gray-white powder on that calcium. So it doesn't look like I think it would. The lab says for us to put it in the water. So I'm going to go ahead and do that. And I believe the lab says we're supposed to cover it up with a watch glass, which we have here. We have watch glasses for each one. So I'm going to put the calcium into the water. And in terms of observations, I am seeing some bubbles happening. It's bubbling pretty slowly here, but it's kind of neat, actually. It's creating bubbles all around the calcium. So the bubbles underneath the calcium are actually pushing it around, almost like it's a puck on an ice hockey table. Mr. Park, does it look like it's getting faster, or is it staying the same speed?
No, it's speeding up.
Okay, so I'm actually seeing, I don't know if you guys can see this at home, but I'm seeing pieces of what's like the white outer flaky part of that calcium. I'm seeing it kind of fall away as this reaction gets faster and faster and faster. If I pull away the top, you can hear it now. You should also be able to see that there is some sort of vapor coming off. I'm going to feel the beaker. The beaker is definitely warm. Definitely warmer than it started. So we have some sort of vapor, some sort of gas coming off. We have an increase in temperature, and looks like the reaction's done. Now it also says we're supposed to put in some phenolphthalein. Now phenolphthalein is something called an acid-base indicator. Its job is to turn a different color when it's in the presence of an acid or a base. So this will turn a pinkish reddish color, purple reddish pink color, whatever, depends on the mixture, when it's in the presence of a base. So I'm going to squirt a little bit in here. And you can clearly see that that mixture that was a cloudy white has now become pink.
Would that have turned pink before we added the metal?
I don't know, let's check. Let me just put some water. I don't have another beaker handy, but I do have just a weigh boat. Let me just put some water in a weigh boat. Nope.
So the water itself is not a base or an acid.
So something that metal did in that water, something when the reaction must have created a base of some sort. Now we haven't learned about bases yet, but you might need to do a little research in the lab to answer one of the questions regarding that color. Okay. Next, it says we're going to put in magnesium. Okay. And we're also going to do aluminum. Now these two, we're gonna do them at about the same time, and we're going to come back later and take a look at them. So first, magnesium. Magnesium I don't need to use tongs with, but I will anyway. Let me get a nice big piece. Here we go. So here's a piece of magnesium. Comes in ribbon like this. And hopefully you can see it's got a little bit of that shiny luster that we typically associate with a metal, but it's not perfectly shiny. Looks like there's little streaks of black, little veins of black coming through. There's definitely a darker smudge of black right there. So the lab says that if the metal isn't shiny, to go ahead and take sandpaper or steel wool. I've got a piece of steel wool here, and I'm just going to run it along the magnesium a few times, and you can see that it definitely got shinier. I didn't get rid of all that black, but this side's pretty clean right here. So when I did that, I was able to shine that metal up. There we go. You can see the difference on your left versus your right. So make sure you're making observations about that. When we got it out of storage, it was definitely kind of a dull metallic look, and now it's definitely a shiny look, okay? I'm gonna pop that into the water. Mr. Park, you might wanna stand back. This could be dangerous. Oof. Not nearly as exciting as the calcium was.
We might need to come back to this one.
Yeah, let's let that one go for a little bit. The last metal is what we're used to with typical aluminum foil. So here we have just a little piece of aluminum. Okay, and you can see this, nothing has to be done to it. It is shiny. You can actually almost see a reflection in it. So you guys are familiar with aluminum foil. So if you're making observations, right, you can observe how that looks. Doesn't look like there's any little black smudges like the magnesium had, and it definitely doesn't have a coating across the whole thing like the calcium did. I'm gonna pop that into the water. Whoa! Okay. So we're gonna cut the video here for a little bit, and we're gonna come back. Okay, and we're back.
All right, Mr. Tro, let's look at our metals that were sitting in water. You zoom in real close to the magnesium, maybe over the top. You see those speckles on the surface of the metal?
Yeah, it almost looks like the surface is kind of hairy.
Now, if we give this a little tap, you should see the bubbles coming off.
Yeah, let me go around the side here.
Now, these are definitely not as many bubbles as with the calcium.
No, but I can definitely see the bubbles on the surface of the magnesium. They're still stuck to it.
Okay.
Okay.
So I wonder if this water turns basic as well. Let's try the phenolphthalein.
All right, so you're gonna put a little phenolphthalein in there.
Yep. And there's a tinge of pink. I do see that.
Like right on the edge of the magnesium?
Yep.
It's really hard to see this. Let me turn this around.
You need the white underneath.
Oh, now I got some good bubbles. Oh yeah. Definitely have bubbles on the surface there I can see. And yeah, definitely a pink color. Okay, but it's not dramatically pink like the calcium was.
No, just a little bit.
Okay.
All right.
Well, that was really exciting.
Let's look at the aluminum.
All right.
And I don't see any hint of any bubbles.
No, nothing's on the surface.
Just looks like aluminum. Let's try the phenolphthalein.
Sure. Now look really closely on the edge. Do you see anything?
I don't see anything.
No. And you're not colorblind, so I believe you. So, Mr. Park, why don't we recap what we saw with these three?
All right. So the calcium reacted vigorously with the water. There was lots of bubbles, and we saw some cloudiness, and we saw gas. Lots of gas. Well, if we saw bubbles, then it means gas.
Right.
We added the phenolphthalein, and it turned bright pink, which means the solution afterwards is very basic.
So there's probably a question in the lab that asks them about that, and then maybe has them determine what kind of gas might have been produced.
Yeah, they'll have to use their powers of deduction for that. The magnesium reacted with water slightly. We did see bubbles, and it reacted with the phenolphthalein to a small degree. We did see some light pink. So this solution is minimally basic, and there was a reaction, but it wasn't anything close to the level of the calcium. And then we looked at the aluminum. There was basically no reaction with the water, as well as no reaction with the phenolphthalein.
Gotcha. Now I'm actually going to take a little field trip. I'm going to look at the periodic table here that's in the classroom section, and finding the metals. Mr. Park, can you point to the metals we're doing here?
So we looked at calcium,
Gotcha.
magnesium,
Those are on top of each other, so they're in the same column. We call those families.
right? And aluminum is in the same period as magnesium.
Okay. So we can actually compare and contrast horizontal reactivity trend and a vertical reactivity trend. Okay. Let's move on. Let's take a look at what happens when we react these with the air in the presence of a flame. Okay, we're back for part B, but before we actually do part B, since you guys haven't been in school yet, I thought maybe Mr. Park could give you a little tutorial on how to use what's called a Bunsen burner.
All right, this is your typical lab Bunsen burner. And the burner has two adjustable points. The first point is the valve underneath.
Okay.
This controls the gas flow that comes into the burner.
Gotcha.
And then the second adjustable point is the actual cylinder itself, which turns, right? We can spin it and turn it. And if you look closely, there's a little air gap.
Sure.
And the more I turn it, I'm turning this counterclockwise, the bigger the air gap gets, which means more air, more oxygen gets in, and that ends up making the flame hotter.
Because when you burn things, you need oxygen. Gotcha.
I'm going to go ahead and connect the hose. This is your gas jet. This is connected to the natural gas line, which is the same kind of gas that you have in your home.
And I see a valve here. So when it's 90 degrees to the hose, when it's 90 degrees to the gas jet, that's off?
Yeah, perpendicular in plumbing is always off. Parallel is always open.
So if we wanted to turn this on, we would put it parallel.
Right.
And if we went all the way again to the right,
then it's
off
perpendicular again, right?
Okay, that's nice.
Okay, so to light the burner, I usually strike the match first and then turn on the gas.
Gotcha.
In that order, because if we turned on the gas and then waited a minute and then lit the match, possibly something bad would happen. Use your imagination.
I've seen videos on YouTube of people lighting gas grills that way. Okay, so wow, that's a pretty nice flame.
So we left the
Let me turn the lights down just a little bit so we can see it.
We left the aperture open on the bottom, so that means there's a lot of air getting in. So this inner cone is really, really hot. We don't need the flame to be that hot for the purposes of this lab, but some labs you will need a hot blue inner cone, and this is what you're looking for. If I turn this clockwise, I'm closing
the barrel,
right, and less oxygen gets in, and you notice how the cone sounds less angry.
Yeah.
And it almost blends
gone
away.
now.
Yeah, it's almost
now
gone.
I don't see a cone. I just see a nice blue flame.
This is what we call a cool blue flame. This is your typical flame that you'll be using for most of your labs.
Well, how come it doesn't, I know when I light a campfire, it's all yellow and wavy.
Well, if we keep turning and close the oxygen intake.
There it is, kumbaya.
Yeah. This is actually not as hot as the blue flame, and we don't want to use the orange flames because this will end up charring the outside of glassware.
Ew, okay.
So
for our labs, we're either gonna have a cool blue flame like that.
Yep.
What if that flame's too high now? What if that's too much gas? Is there a way to close down?
So there's two ways. You can either adjust the intake at the bottom.
So you turn the valve or the diaphragm down. Gotcha.
Lower the height of the flame.
Okay.
Or if it's just too much flame, you can turn it off by adjusting the valve at the source by turning this more perpendicular.
Gotcha. Okay.
Okay.
Now for the lab we're doing here, for part B, what kind of flame does it call for? I believe it's a hot flame.
Is it a hot flame? I believe it would work with either, but we'll go ahead and
we'll go with a hot flame.
Okay.
You know, when in Rome. All right, so you got the gas going in at a good rate.
There it is.
Perfect.
Okay, so we're gonna react magnesium in the flame.
So you're gonna put the magnesium right in the tip of that inside cone. That's the hottest part of it.
Right.
All right, let's take a look. Ooh, oh, whoa, 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 that's bright. It's crackling. Can't even really focus on it. It kind of looks like a meteor entering the Earth's atmosphere. Wow, okay. So when you, when you started, the magnesium was a silvery, shiny metal, and right now it's kind of like a white, crusty looking, almost powdery. All right, why don't you drop it into the water? So I still see a little silver in there.
We'll put it over the black, but I hope.
Ooh, there's definitely flecks of powder, right? You can see how that metal was once one piece, now it's broken into multiple little pieces, and there's little flecks of powder everywhere. Okay.
So that's some phenolphthalein.
Sure.
And if you see,
Yeah.
there's a little bit, faint amount of pink there.
Faint amount of pink right around. I can see a little bit of pink in the middle by the powder that's on the bottom.
Come at you from the side, maybe get more light.
Oh yeah, there we go. Good call. That's definitely got a pink color to it. So when it reacted with the water, it created a substance that would turn phenolphthalein pink. And when it reacted with the air, it also did the same thing. Or whatever it created when in the presence of water allowed it to turn phenolphthalein pink.
Essentially, once magnesium comes into contact with the water, either reacted or not, I think it's easier to see the pink when it does react.
Sure.
Okay. This is aluminum,
Shiny.
just like before.
Yeah.
Let's see what happens when we...
Oh man. Should I stand back? Oh, it's kind of dancing a little bit.
Oh, it's just because it's a thin piece and it's almost melting. And
I
so
see it's curling up a little
looking
bit.
charred a little bit.
It's not flaring up super bright like the magnesium did.
No, there's no.
So I see a slight change in color, but that's probably just the metal getting really hot.
Yeah.
So it definitely got a dull glow. It didn't flare up super bright.
We got some reactivity, but there's no flaring up, right?
Yeah, if you look at the surface of that aluminum, it's kind of dull now. It's not nearly as shiny as it started as, but it doesn't look all powdery the way the magnesium did.
All right, so let's drop it into the water.
Oh, flipped over. So that was the side that wasn't exposed to the flame.
There it is.
There it is. Yeah, so it's still fairly shiny. You can see on the left side of the metal, I don't want to use the word for it, but it seemed to have reacted in the presence of the flame. Okay.
Here comes the phenolphthalein. And not much.
Is there any pink color?
No, I actually don't see any.
Okay. So not like here, you can definitely see the pink with the magnesium. The alumina has none. Okay. Okay, for the third part of the lab, we're going to take a look at some of the metals in this family right here. Now, this is the first column of the periodic table. These are known as the alkali metals. We're disregarding hydrogen. Hydrogen has one outside electron just like these guys do, but hydrogen is definitely not a metal. So we're going to take a look at lithium, sodium, and potassium, and we're going to take a look at how they react in the presence of water as well, and if there's any similarities and if there's any differences between them. Unfortunately, we don't have rubidium or cesium or francium at our disposal, so we won't be testing those. And you'll see, I think you'll see why in just a minute. Okay, so in the previous part of the lab, we were testing calcium metal, and calcium metal just came in a plastic bottle. And we had magnesium, and we stored it in a plastic bottle. The metals we're testing today, we might store still in bottles, but they're not going to just be sitting in a bottle in air. If you notice, here is lithium, and it's definitely stored in a liquid. Now that liquid moves way slower than water does. That's mineral oil. This is oil. So we store these metals in oil, all three of these: lithium, sodium, potassium. They're all stored in oil. Okay? So we're going to take a look at what happens when we put these in water. Before we do that though, we have to remove them and get a little piece. So I know when I think about metals, like a piece of iron, I think about something being shiny and hard. Oh, excuse me. Right? This is definitely not that shiny. There is a little shine to it, but it's mostly the oil that's on it. So if we actually take a look, I can scrape away part of the outside where the oil is coating it, and you should be able to see that there's definitely a shine there. And shortly after I strike it away or swipe it away, the shine kind of dulls a little bit. So there's a coating on the outside of this metal. This one still looks, though, a little metallic, but there is a fine coating on it. So one of the cool things about alkali metals that you wouldn't expect is you can actually cut them. They're soft metals. Now, right where I cut that, if you look where it's exposed, definitely not shiny. Where I cut it, it's got quite a bit of shine to it. Okay? So we're going to take this now, we're going to walk it over. We're going to do this reaction in a fume hood. This is a fume hood. It has a fan inside. It's designed to suck any gas that's created out into the ceiling, out of the room for us, keep us safe. We've got a beaker here of water. I'm just going to pop this lithium into the water. Now, Mr. Park, that reminds me a little bit of the calcium, but it's definitely reacting a little more. I see, you can definitely see there's a vapor, there's a gas being produced. I'm gonna touch this really quick. The beaker's getting warm. Beaker's definitely getting warm. We have gas, you can see it being sucked out. I would say that's reacting at a pretty good pace. Nothing that I have to be scared of, but it's definitely reacting. Okay. And I can put a little phenolphthalein in there with it. And you can see that it quickly turns that pink color. So we're back now. We just did lithium. Now we're going to do sodium. Sodium is also kept under oil. Now when I pull the sodium out, take a look of how it's different. How it looks different than
It's not as shiny.
lithium. No, there is it glistens a little bit. That's the oil. That's the light hitting the oil. But this is not metallic looking at all. This has almost like a white or a gray coating to it.
It looks like cream cheese.
Yeah, kind of. If we scrape it, you can see that it turns metallic right away. And after a few seconds, the luster kind of dulls down again. Now the other one, when I cut the lithium, I had to push really hard to cut it, but I was able to get through it. Same knife, and you can see that cut so much easier.
It's like butter.
Like butter. Shiny where I cut it, and you can see that it oxidizes over right away. Shiny, dull. So this seems to be reacting with air pretty fast. Okay, let's walk this piece over. We have a fresh beaker. This is a clean beaker of water. Same temperature as the other water. We'll pop it in. And the first thing I notice is that is reacting much faster. And it caught on fire. You see the flame? It's sparking, or sparks shooting out of it. Whoa, that's fun. Okay. Good thing we had that safety shield in front of us. You feel it? Yeah, definitely warm, definitely hot. You can see that there are pieces of sodium that's shot all over. Let's test it with phenolphthalein. Looks like it also had a reaction that turned it a pink color in phenolphthalein.
So this reaction was just like the first one, but this one was over a lot faster.
Yeah, it went much faster, and it actually, I guess it produced enough heat to actually start a fire. So whatever gas is coming off of these reactions, the same gas is being produced with the lithium and the sodium. Whatever gas was produced with the lithium, there wasn't enough heat to actually ignite the gas. Looks like the sodium had enough heat to light it. Kind of like a match, you need to strike a match, you need enough energy to light it. There was enough activation energy to light that gas. Now with our third alkali metal, this is potassium. So I'm going to take a chunk. This is a big chunk. Wow. So now this actually has multiple colorings to it. You can see a part where it was touching the bottom of the container.
I think that's where I cut it last.
All right. And then it is all corroded. This almost looks like if you were to find an old rusty pipe. very, very reacted on the outside. Doesn't even look like a piece of metal. Right? If we cut it, really easy, even easier than sodium. Very shiny on the inside. You scrape it. You can see how where I scrape it, it turns shiny and then it immediately coats over. So whatever this metal is doing, it's reacting with something in the air almost immediately after we scrape it. Okay? All right, we'll put this one in the water and see if this reaction goes faster or slower than the previous one. Okay, here it is. Oh, and that caught on fire immediately. Wow, what colors are those flames, Mr. Park?
They look violet.
Violet. The other flames were violet. Oh, hello!
I'm okay. That was scary.
So you can see when we put that in, it reacted immediately, and it caught on fire immediately. The sodium took a couple seconds. It was sparking, and then it took a couple seconds, then it ignited. The potassium ignited right away. Burned super fast. It was over in about 5 or 6 seconds. And it too.
Very basic.
And it's a warm. The beaker is warm. Now, if you notice, if you compare all three, the lithium just kind of fizzed. The sodium caught on fire eventually and burned faster, and some sparks were flying out. Some flaming bits were flying out. And then the potassium caught on fire right away, had a purple or a violet hue to its flame, and it shot up, and actually a little piece actually came out of the fume hood and attacked Mr. Park. So,
All right.
There's your 3 alkali metals.